So in this video, I want to talk about a little bit about quantum cryptography. Okay, just to remind you, on our two-state system, we had some state psi, which we said was something like alpha 1 up, if we put it in the up-down basis, plus alpha 2 down, right there. And when we had the 2 bits, let's call this our first electron, or our first qubit. The second one, we used beta here instead, beta 1 up plus beta 2 down. And then when we combined the two into a composite system, remember we did a special tensor multiply. So we said psi 1 tensor multiply psi 2. And then we just multiplied it all out right here. And so this was alpha 1, beta 1, up, up. We always do this one first. Up, up. Plus alpha 1, beta 2, up, down. Plus alpha 2, beta 1, down, up, plus alpha 2, beta 2, alpha 2, beta 2, down, down. Okay, so we said these were all just a two-dimensional, but now when you tensor multiply, it became a four-dimensional. If I were to write this column vector out right here, this column vector, the four elements would have been this one, alpha 1, beta 1, alpha 1, beta 2, alpha 2, beta 1, and alpha 2, beta 2. Those would have been my four-dimensional column vector. Okay. And we called this a product state because we could have factored it back into just the product of the two. But we did say there were some that were not factorable. Namely, one we said was 1 over the square root of 2 up, down, minus 1 over the square root of 2 down, up. We said this was a quantum entangled state, which meant if you measured the first one up, the second one would be down, or if you measured the first one down, the second one would have to be up. This is one quantum entangled state. Another one, I guess we could have said 1 over the square root of 2 up, down, plus 1 over the square root of 2 down, up. Or we could have said 1 over the square root of 2, say up, up, plus 1 over the square root of 2 down, down. Or the last one here we could say is up, up, minus 1 over the square root of 2 down, down. So these are all maximally quantum entangled states. And we said that if we had something like, we said we had a pi 0, it's decayed into 2 photons, and their total spin has to be 0, so if one is up, the other photon has to be down. These two would follow this one right here. So you get these two states right here. You get and so these would be the two states of the photons, and we showed last time that they don't decide what they're going to be until they're measured. One of them's measured and then the other one. So if you measure this one up, all of a sudden this becomes down. If you measure this one right, this one all of a sudden becomes left. If you measure this one in, this one all of a sudden becomes out. And we went over the Bell inequality where you measured these at two different spots and correlated with these, and we found out that that these did not make up their mind. There is, locality is broken. These things can communicate with these even over the size of the universe, instantaneous, right? But we can't use that, at least here, to our advantage. We also said if we had 3 terms, then we would have 8 of these. You'd have a column of 8 numbers here, and you'd have like up, up, ups, and up, down, ups, and so on. And we said if you had 300 terms, then the 300 of these qubits right here, then you'd have 2 to the 300 terms, and that's more terms than there are particles in the universe. And it's all the number of these, since they're so huge, that helps with quantum computing because it gives you a huge scratch pad. It gives you a scratch pad that's bigger than the number of electrons in the universe, just with 300 qubits. Now, that sounds good, but the only thing is you don't get to see these right here, right? With a quantum computer, you initialize a state, apply some fields and stuff, and let it collapse into a final state. So you don't get to see the scratch pad. Okay. And there's something else in here about states like this. There's a theorem, it came up in 1980s, it's called the no cloning theorem. No cloning. Which means you cannot make a copy of this right here. You cannot record it. You know, it's not like regular data. You can record as many copies as you want. Here, you cannot do that. It's called no cloning right here. We'll see with teleportation, if you want to make one copy, you got to destroy the original. So you're not really creating any more copies right here. You still got the one copy. Okay, and that helps you with quantum cryptography, which is sending secret messages between 2 people. Now, with classical systems, it's impossible to be 100% sure that you can send a signal without someone else intercepting it. It's impossible with a classical system, but with a quantum system, it is possible. Right? It is possible. They actually determined it in 1984. 1984. These are all quite recent. 2 people. One, Bennett from IBM in Bussard from the University of Montreal, figured out a way to send an unbreakable code. They called it the BB84 because their 2 last names were B, and the year was 84 on quantum cryptography. So let's say we want to send a message between 2 people, Alice and Bob. So we've got Alice here, and we've got Bob over here, and they want to send a secret message without someone intercepting it. Here we'll have someone trying to intercept it. This will be Eve. She'll try to eavesdrop right there. Okay, so what happens? Well, first of all, what do you send right here? Well, one of them is the message. The message that you don't want Eve to detect. The message. Now, these are just going to be bits right here. Could be just 0, we'll say 1, 0, 1, 0, 1, and so on. It's just a sequence of bits right here. Now, these could be text, it could be sound, it could be movies, it could just about be anything right here. You can digitize right here. So that's what you want. That's what she wants to send from Alice to Bob, is this message right here. But to do that, you have to have a key right here. A key. Right here. What's the key? Key is just a sequence of bits too, right here. Let's just say the key was 0, 1, 1, 0, 0, 0. Let's say that's the key. So this is the key. That's the message you'd like to send. So, but you have to send a coded message. So we have to send actually the ciphertext. Cipher text. Okay, and so what you do is you just add these two together right here. Now when you're adding in binary, 0 plus 0, we're just going to call it a 0. 0 plus 1, we're just going to make that a 1. 1 plus 0, we're going to make that a 1. And 1 plus 1, we're going to make that back to a 0 again. So that'll be the way we're going to sum these up. No carries or anything. Okay. So if we just add these up, 1 and 0 is a 1, 0, 0 is a 0, 1, 0 is a 1, 1, 0, 0. Okay. Just wanted to, yeah. Okay, so now this is what is sent. This is what is sent from Alice to Bob right here. That's what they'll eventually want to do. And then what does Bob do when he gets these bits right here? Well, he knows the key too. And so what he does is he says, okay, I'm just going to take the key and add it to this, which is 0, 1, 1, 0, 0, 0. Okay, which is 1, 0, 1, 0, 1, 0, which is the same as the message. Okay, so the important thing is, the thing that really has to be kept secret is the key. The key, this can be public to everyone right here, you know, because you can't get the message out unless you have the key. So everything is down to key distribution. How do you get the key to both of these two? Because they won't even send the message until they're both sure that they both have a key that's secure. So it really comes down to key distribution. Key distribution. So if they both know they have a safe key, it's done right here. Okay, so what does Alice do right here? Alice is going to start sending some, she starts sending some bits right here, qubits across. And she's going to keep a record of what she sends. So let's just say she sends, say, an up. Then she sends, say, a right. Then a left. So she's going to remember which one she's sending. An up. And she's only going to send things between up and down and right and left. No ins and outs. Just up, down, right, or left. Just random down. I'm just going to pick some right here. Then how about left? Another left. And up. Okay, she just randomly sends out up, rights, lefts, and downs. That's all she's doing right there. Okay, but she keeps a record. She knows what she sent right there. Okay. Now, Bob at the other end doesn't know what she sent right there, but he's going to measure these with his sensor, and he's either going to measure them in the Z direction, which means he's measuring up or down, or he's going to measure them in the X direction, which means he's measuring right, left. So he's either going to measure Z, so he's just making a Z or an X measurement. So let's just say he randomly makes a measurement. Z, X, Z, X, X, Z, Z. That's all he's going to do, is just randomly make these right there. Okay. Now, what does he measure right here? Well, this first one, since he's got his sensor in the same direction as this up one, he's going to measure a +1. right here. Well, since he's got his sensor up and there's a right there, that means he has a 50-50 shot of measuring a +1 or a -1. He doesn't know. He's just going to pick, he's going to get one of them. Let's just say it's the -1. Over here, since he's got his sensor hooked up this way, if he measured a right, it would have been 1. Since he measured a left, this one would automatically be -1. Since this is Z in the Z direction, he would get a +1 here. Over here, X, this is measuring right and left, but he put in a down here, so this would be a 50-50 shot. I don't know, let's just say it's +1. This one over here, since it was in the X direction, that's the right left, so he would have gotten a -1. Over here, since it's in the Z direction, and this is left, it's a 50-50 shot again, so let's just say +1. And then this one would be a +1 because it is in the up direction right there. Okay. So that's what he would measure. Okay. So now Alice and Bob get on the phone. Okay. And they have a public conversation. That is, Eve can listen in on the conversation. It does not matter. So Alice and Bob talk on the phone. Talk on the phone. Okay. So what does Bob say? Bob says to her, he says, I made these measurements. I made the Z, then the X, then the Z, X, X, Z, Z. Those are the measurements I made. Now, what Mary says is, she said, this was a good measurement because the Z actually ended up with the up. So she's going to say, that's a good measurement right here. This one right here is not a good one, right? That's a bad measurement. So maybe I'll put that one in red. That was a bad measurement. This one right here, it's in the X, and for the L, that's a good measurement. This one right here, that's a good measurement. This one, that's a bad measurement. This one over here, that's a good measurement. That's a bad one. And the last one's a good one. Now, she hasn't given any information to Eve over this. She's just saying what's a good measurement right here. Well, that way, first of all, they can get rid of all of the bad measurements. So they already know, Alice and Bob know which ones are the bad ones, so they'll throw out this one, throw out that one, and throw out that one. And they will, this one, anytime you see a 1, +1, we'll just call that a 1. Anytime you see a -1, I guess we'll call that the 0. This one is a good, that's a 1. This was a -1, so we're going to call that a 0, and then this would be a 1 right there. Now, Eve, if Eve tried to intercept this message right here and tried to measure them on her own, and tried to measure these, she would mess them up right here, because if she tried to measure, say, one of the states along the X and it was really something like an up, she would mess up the state. So her making the measurement would affect this right here, would affect this. And so now what Alice and Bob are going to do is they have a whole string of bits right here. They'll take a small sample of them. Take a small sample of them and say, I got 101101110. And Alice and Bob will say, I got that same string. What that tells them is that Eve could not have intercepted this because she would affect the measurement right here. So once they have a subset of it correct, then they'll know, well, then the rest of it must be a good key. This must be a good key. And now I can use that key distribution between the two, and we can send the text. Once you have the key distribution, you have it right here. So now the one thing is you got to keep sending new keys out. You can't use the same key all the time because then you'll be able to figure it out. But every time you take to send the message, you just figure out the key first and then add it to this and send it. Now they actually have commercial devices that you can buy, a box that will use photons sent over long distances, and they can use the polarization to do this. Now, who's doing this? Probably big banking institutions and things like that. They're probably not cheap right here. But this way, you get 100% secure information is sent between the two groups, right? I'm sure the Defense Department has some of this stuff. Unbreakable codes right here. Okay, just to show you a nice outcome of quantum cryptography, and before 1984, they never really wondered about what are the good things about quantum mechanics. It was always limitations. You have the uncertainty principle. But after 1984, they started to think about what are the positive things I can now do with quantum mechanics. Okay, so hopefully that explains one way of sending a 100% secret message that's 100% foolproof. Okay.